Hello, this is a mini lecture on Smith chart, and hopefully it will serve you well. And so basically what was given in class was just a brief few equations on voltage standing wave ratio, or VSWR, and how it's related to the reflection coefficient value and the impedance, input impedance, and the admittance values equations. But this tutorial is really on the Smith chart, so just to give you so that we can quickly see what kind of equations we'll be dealing with. For example, would be, let's say, uh, voltage standing wave ratio, and this is just equal to 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. It can easily be seen that the ideal case, it's easy to see that the ideal scenario would be VSWR equals to 1, and that is obvious because it's the ideal case will be if your reflection coefficient being 0, which is obviously, this cancels out and you have a voltage standing wave ratio of 1. That'll be the ideal case because then you have all the energy transferred from the transmission line to your load, and this is what we desire basically. And then this tutorial is nothing to do with impedance matching to fix the problem of reflection problems. However, this tutorial is just to get the values of the reflection coefficient and voltage, standing wave ratios, and input impedance and input admittance example. For now, this is what really voltage standing wave ratio really means, and obviously the reflection coefficient would be, for example, the reflected wave. Can use another color for that one. Reflected wave over the incident wave, and also it's usually equal to the load impedance minus the transmission line impedance. Same thing, but it's a positive. So that's what was given in class, and we really want all the power reach its destination, and that only happens when reflection coefficient is 0. So we can also write the reflection coefficient as, if we relate it to the voltage standing wave ratio, and again, best case would be okay. Now that we know this, and we know the impedance, which we refer as Z, has the resistance value, and it has the inductance or capacitance component, and it's to do with the changes in current in AC. So, and really, it's really the opposition. It's a measure of opposition to a change of current or voltage of a circuit. And we would see this all in the Smith chart. So the reactance, we have the reactance value component, we can say. Sorry, not the reactance, that's not the reactance. That's the resistive, as I said earlier. That's the resistance component. And this one will be the reactance component. And these will be on the Smith chart. And now use another color for this one. Your admittance value would obviously be 1 over the impedance, and it's very useful to use in some problem solving, as I'll explain later during the Smith chart demonstration example. So we have 1 over R plus JX, and if you solve this, it's just equal to R minus JX over R squared plus X squared, and this is in Siemens, the unit for it. So usually it's given as Y equals G plus JB, where G is the real part conductance, and B is susceptance, and it's the imaginary part, obviously. So these are usually the values that we need for our example that's coming shortly, and this is what we'll be working with. And this is the first time I'm actually using Smooth Draw to do this tutorial, so you might see me pause a few times, and I haven't had practice with it, so I just wanted to go right to the tutorial. So for now, I'll just pause my recording so I can get a new page. So now I'm back, and the example would be for the Smith chart example would be as follows. If we can use any color for now. We can use blue. So usually my favorite color with the green. We have a 50 ohm lossless transmission line is terminated in a load impedance ZL equals 25 plus J 50 ohms. Now the question will be, use a Smith chart, or just use Smith chart to find the following. A, reflection coefficient, or the gamma, and B, voltage standing wave ratio, or VSWR and input impedance or Zn, and finally input admittance of the line or Yn. So that's what we need. We need these four values without using the equations. However, we're using the Smith chart, which is a very useful tool without having to solve the problems using the equations. And however, before I start with the Smith chart, I just want to get the normalized Z value, the normalized ZL value, which is normalized impedance. Uh, Actually, the normalized usually it's small z. However, let's just call it normalized. It just equal to the value, which is the 25 plus J50 ohms over the 50 ohms of the lossless transmission line. That's how you normalize your load impedance. You end up with a 0.5 plus J1 without unit. So they cancel out. So we need this value in our Smith chart example coming very shortly. So now that we know what the question is, we can go on with the example. First, we know we should get the normalized load impedance, which we discussed was ZL equals to 0.5 plus J1 ohms, and we need to get the reflection coefficient. We can actually use a different color for that one. Can use this blue, and then we need to obtain the voltage standing wave ratio, which is VSWR. Can use this color, and we need the input impedance. Can use this green, and the input admittance, which is abbreviated as YIN. Okay, now we can solve these without the equations using the Smith chart. We'll start with the reflection coefficient, but before we do that, actually we should draw the normalized load impedance. And before we start drawing this, just a quick review of how the Smith chart looks like. You have the resistance component down here, which is the x-axis, the whole thing actually, and then you have the inductive reactance component, or the capacitive susceptance component, and you get the negative end on this side. And so these components are very important to actually draw your impedances, to get the points for your impedances. And you get the angle of reflection here. That's a very important one to solve your reflection coefficient. And another important part of the Smith chart will be the wavelength toward generator, which is important in solving the input impedance. So now that we know these general areas of the Smith chart, we start with drawing the points. So let's start with the normalized impedance, which is 0.5 plus J1. So by 0.5 will be obviously the reactance component. So we look at the reactance component as mentioned earlier, axis, and it's 0.5, which is this point. That's 0.5. You keep going. This will be the line for 0.5. That's the curve actually for 0.5. You keep going all the way to your J1 part, which is the inductive reactance component. So that's your 0.1, and that's the curve for 0.1, and wherever they meet, which is this point, will be your point that we're looking for. So we don't need this extra lines here because we need to draw a lot of things in that Smith chart. That was just to demonstrate how you get this point. This is the point we're actually looking for, which is the load impedance, normalized load impedance. So that's your point ZL, which is the normalized load impedance. Now that we've drawn the normalized load impedance, we go into the reflection coefficient. Now the reflection coefficient obviously has an angle and a magnitude in polar form. This is where you get the angle of the reflection, as I mentioned earlier. We go to the color that reflects that. So we need to figure out this load starting from the origin. I'm gonna try to draw a straight line. I don't have a ruler for this. Maybe it's possible to use a ruler in this program. I'm using Smooth Draw. However, I'm using for the first time, so I'm just gonna draw the line that would cross the normalized impedance, load impedance, and we keep going to an approximate angle of coefficient. So that's the angle of coefficient as you see here, which is this line. So it'll be around 83 degrees. So now we know the angle is 83 degrees. We need the magnitude. How do you get the magnitude? Is basically you divide the length here over, like literally over the length of here. So it's a ratio. If you use a ruler and you actually divide the length here, which I can call the length, let's call this length d, the distance or length, whatever, dzl over the r for reflection coefficient. And if you use a ruler literally and then measure the ratio of length between those two, you will end up with approximately 0.62. so that would be your magnitude. It's as easy as that. So just to write it better, left more space. If I left more space it'll be better. However, I can do it right now. 0.62 with an angle of 83 degrees. So now we have our reflection coefficient. Earlier it was an equation. So now we don't need that equation. Smith's chart just literally gives you that value, which is very convenient. That's why it's sometimes called black magic. Now as we go back, now we need to get our voltage standing wave ratio. Now this voltage standing wave ratio is easy to get obtained from the flow chart, from the Smith chart, sorry. As you notice, I did the dots earlier because I don't have a compass, but you will need a compass to actually draw a circle starting from this ZL point and ending at that ZL point as well. It's not a perfect circle obviously because I'm drawing it by hand. At least I'm trying to. Tracing those little dots that I had earlier. Alright. Usually this circle is actually called the VSWR circle. So it's the voltage standing wave ratio circle. And as we know from the equation I gave you earlier, the VSWR is equal to 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. Hence, it's usually greater than 1. And the ideal case will be a 1 because that will have a 0 reflection coefficient. But since that's not the case, it's usually greater than 1. So it's the value that actually crosses the resistance component from this side. So this will be your value for VSWR, or voltage standing wave ratio, which is approximately between 4 and 5, or to 4.2, maybe 6. So 4.26. So 4.26 for VSWR value. That is it. No equations, nothing. We just got the value right from the Smith chart. 4.26. So now that we have our voltage standing wave ratio, we move forward for our input impedance. And the input impedance also can be obtained directly from the Smith chart. What's from the question we have I have mentioned that that it's given that the line is 3.3 wavelength long. And if you notice, again, because now we're working wavelength towards generator, which is this part of it, we can notice it starts at 0. Maybe I should move to the color. We can see it starts at 0, and then if you go around that whole circle, it goes 0.49, and then so obviously it's 0.5. So a full circle is 0.5 wavelength long. So if the question is asking for 3.3, obviously you're gonna go 0.5 once, 0.5 twice, 0.5 3 times, all the way to 6 times. 6 times of a full circle gives you a whole 3 wavelength long, and we're remaining obviously with 3.3 wavelength long minus the 3 wavelength long. We'll end up with a 0.3 wavelength long. So now we're working with a 0.3 wavelength long. We can keep those, doesn't matter. So now how do you move 0.3 wavelength long? The value is actually at the ZL, which is the same point, ZL point, load impedance. You keep drawing all the way here so that you'll be at the curve of the wavelength with generator, which is approximately 0. As you can see here, 0.13 and a bit more, 0.135. So you start at 0.135 and then you add 0.3. So by adding 0.135 wavelength plus 0.3 wavelength, you end up with 0.435 wavelength. And this is exactly what this will be the exact point. So let's try to draw this here. So it goes all the way. We need to find the point 435. So it's approximately here. Now that we have moved 3.3 wavelength toward the load, towards the generator, we end up with, you draw the line to know where the point is, which is approximately here. So now I have a new point which we can call Zin for input impedance, and now we've obtained our input impedance point on the Smith chart. And similarly, how we initially started with a value for the load impedance as 0.5 plus J1. We drew it here. Now we have the point, we do it in reverse, we obtain the value, and the value is the same here as you need the resistance component, which would be approximately, if you draw it here through the curve, you end up with 0.22426. It's really here, so you can go all the way to, we can say 0.2 or 4.3. It's an approximation, so it'll be like 0.2 4 approximately for resistance value. Alright, so we can write this down here, 0.24. we got a resistance value component, and now we need obviously the reactance component, which obviously it's easy to see it here, it's a 0.4. It's this value, 0.4, but it's on the negative side of the Smith chart, so instead of a plus here we have a minus J.4. Now, it's very important to note here that this value is normalized, because we were working with normalized Smith chart components. So it's logical that we need to multiply by what we divided initially with the load impedance. We divide by 50 ohms. Now we divide by, we multiply by 50, and there shouldn't have been units here. However, it's there. I'm not going to go back at the beginning of the video. However, it's no components. You multiply by 50, you end up with your value, which is approximately maybe 14 minus J20 ohms. This is where the ohms come in. And this will be your actual value for your input impedance. Normally we work with, it's easier to work with admittance, and this is obvious when you start working with impedance matching, where you have parallel lines, and it'll be easier to work with admittance. This is one simple example. However, for now, we just want to know what the input admittance will be, which is obviously the reciprocal of what we already know, the impedance. So how do we obtain this? Is basically, since it's the reciprocal, we just draw a line opposite trying my best to draw a straight line here. The line here, which is at the opposite end, going through the origin. Hopefully I did it right. Gonna try my best. And it's approximately at this point, which will be your input admittance. And again, similarly, to get the value, you have to find the resistance component, which is approximately 1.15. And your reactance component, which is approximately 1.6 or 7. And so yeah, the circle is a bit thick, so we can assume 1.7. 1.7, so J 1.7. Now again, it's very important to note that this is a normalized value, and it's logical that we need to do something about this to get the actual final value for admittance. And since the admittance is the reciprocal of impedance, we divide by 50 now instead of multiplication, and the answer would be as simple as just that division, and it will be approximately 0.023 plus J 0.034, and this will be the value for your admittance. So first I'm actually using smooth draw, and I hope this tutorial will help the ones that need it. Thanks for listening, and until next time.